In this video, we're just going to briefly discuss some additional topics that we don't have enough time to cover fully in the class. So the first is multi-stage circuits. So just like with our BJT circuits, typically we're not going to be able to meet all of the requirements of a given problem with just a single MOSFET stage. And so this is most clearly seen, I think, with amplifier circuits, and we'll talk about those in the next unit. But the same basic idea holds for other things such as digital logic and the other applications as well. So, maybe we have one circuit that is going to give us our gain requirement, but it doesn't quite meet our input or output resistance requirements, so we can connect several circuits together. And so the key thing that we saw with our BJTs, which is also true here, is that in reality, we're going to need to consider loading effects. And so that's the main reason why we're going to have to design for a certain input or a certain output resistance, and not just for amplifier circuits, but that's relevant to other circuits as well. So our loading effects are very important. And so if you want to see a little bit more about different circuit configurations in terms of multi-stage connections, you can look on pages 175 to 179 in the textbook. And so that's going to give you details on two types of connections in particular, cascade and cascode. So cascade and cascode configurations of our MOSFET circuits. So one other topic, well actually two topics we're going to cover, but one in a little more detail here is another type of transistor circuit, or rather another type of transistor I should say, which is our junction field effect transistor. And so it's worth noting that there are hundreds, if not thousands, of different types of electric devices. And of course, we're not able to cover even a majority of those. But this is another one that is oftentimes used. So a junction field effect transistor, or abbreviated as JFET, has structure shown here. So here we have two P plus regions and an N region in the middle, and then we have two metal contacts on either side. And so this is going to be our drain on one of our metal contact sides, and this is going to be our source over here. And we're going to tie these two P-type regions together, and that's going to become our gate. So we're going to have these two tied together, and that's going to be our gate. So let me put a little circle here too. So this is also our gate down here. And so what we can see is that we have a channel region between our source and drain, which is this N-type region right here. And so now as we start talking about biases, let me go ahead and add some batteries in here. So let's say we have some gate to source voltage. So let's go ahead and ground our source like we have typically done with our other configuration. So let's connect that to ground. And this is then our VGS. And we can also connect some potential or some battery between our drain and ground. So let's connect something like that. And so this is going to be then our VDS. And we can have some drain current ID, which will be flowing in this direction. And so of course what that indicates is we have electrons in here in our N region. And so these electrons are going to be flowing in this direction from our source. Our source is creating those charge carriers, or supplying them rather, and they're flowing towards our drain. So let's talk about how we can control the current between our source and drain terminals via the voltage on our third terminal, because remember that is our basic transistor action after all. And so it turns out that if we apply a negative gate voltage, so if we have some VGS, which is sufficiently negative, what's going to happen is if we look at sort of each part here, we see we basically just have two PN junctions. So if we get a negative gate voltage applied to the P regions, that's going to reverse bias our PN junctions. So we have reverse biased PN junctions. And so if you recall way back at the beginning of the semester when we were talking about PN junctions, if we reverse bias them, we create some depletion region where we can't have mobile carriers. And so what that would look like, so let's change to here. So if this is reverse bias, we're considering this case here, then maybe we have some depletion region that is extending around this P part, these P regions like this into our N region. And of course, there's some depletion region extending into our P as well. Not going into details, but because it's higher doped, it's not going to be extending as far into the P region, mostly in the N region. So what happens if we increase that gate voltage? So if we make it more negative, so it's going to become more reverse biased, and we're going to continue to increase the width of this depletion region. So now there is some certain maximum at which point it's going to not be able to increase, but if we design the device geometry appropriately, we should be able to reach some point where if we have a negative enough gate voltage, we have these reverse biased such that this channel in the middle becomes pinched off. So in this case, our depletion region represented by the blue has closed that channel, so there's no longer any path between our source and our drain. And so similar to our MOSFETs, we would call that pinch off. And so we could draw a family of curves, and so it would actually look very similar to what we saw for our MOSFET and our BJT family of curves. And so if you want to see a little more details about that circuit operation, as well as the family of curves and some of the particular equations, you can look on page 180, and so that's going to be section 3.6 in the textbook. And so one other thing we'll mention really briefly as well is the typical symbol, or at least one of the typical symbols that you might see for a JFET. So if we have the drain up here on the top and our source down here, we no longer have sort of this oxide separation at our gate, but instead we're going to have some gate terminal flowing directly into here. So we would have our representation like that, our arrow pointing in from the gate towards the source, and we still have a VGS, we still have a VDS, and we still have some drain current. So then the last item that I want to just mention very briefly is another type of semiconductor transistor, which is our metal semiconductor field effect transistor. So metal semiconductor field effect transistor. And this one you won't see as often as the JFET, and certainly not as the MOSFET. And so this one typically will be abbreviated as a MESFET. So let's see, we need MESFET. So we get that this is often called a MESFET. And so the basic idea is that instead of a PN junction like our JFET, and instead of the oxide like our MOSFET, we're now using a Schottky barrier diode, or Schottky barrier junction rather, for our gate terminal. So again, we're not going to go into any details with that, but if you want to read a little bit more in the textbook, you can look on pages 182 and 183. Sorry, not 1823, that would be quite a few pages to read. 182 and 183 for a few details. And this is a relatively common device, so you could pretty easily find some more details in other books and other places online if you were interested in that.